In order to build up our shell model, we are going to use ionization energy values and consult with Coulomb's law to see what the ionization energy tells us about charge and distance. Recall that the potential energy V is equal to the negative of the ionization energy, and also that the potential energy V is equal to K times Q1 times Q2 over R. It follows then that IE is equal to negative K times Q1 times Q2 all over R just by using simple algebra. Thus we now have a way to relate ionization energy with our two variables: the charges on the particles, the nucleus and the electron, and the distance between the particles, R. We'll start with hydrogen and helium. Hydrogen is straightforward. We have one proton and one electron. So we have a nuclear charge of +1 and the electron's charge is -1. And we can draw it like this. The value of the first ionization energy for hydrogen is 1.31 megajoules. This is measured experimentally. For helium, we have a dilemma. There are two ways to draw the helium atom. We could have it as in Model 1, where the nuclear charge is +2 and both electrons are in the same shell, or we can have it as in Model 2, where the nuclear charge is still +2, but the electrons are in different shells, and each shell is separated by a distance of r, so that overall the distance is 2r. To determine the correct one, we can predict what should happen to the ionization energy in theory and then compare that to the actual value. We'll use our ionization energy equation and the value for ionization energy of hydrogen to guide us. We'll also assume that we can neglect any interaction between the two electrons. For Model 1, if we assume that the distance between the shell of hydrogen and the hydrogen nucleus is the same as the distance between the shell of helium and the helium nucleus, we can write that the ionization energy for helium is equal to negative K times +2 times -1 all over R, which gives us a value of 2 times K over R. For hydrogen, the ionization energy would be negative K times +1 for the nuclear charge times -1 for the electron charge all over R, which gives us a value of K over R. Although we're only looking at the addition of this new electron, the energy value for each one is the same. So we see that for Model 1, we would predict that the value of the ionization energy for helium would be about 2 times that for hydrogen, since 2K over R is double what K over R is. For Model 2, we will assume that the second shell is at a distance of 2 times R. Thus, for the second electron, we can then write that the ionization energy is equal to negative K times +2 times -1 all over the total distance of 2R, which gives us K over R. Therefore, Model 2 predicts that the ionization energy for helium should be about the same as that for hydrogen. So what is the actual ionization energy for helium as measured experimentally? It is 2.37 megajoules. Although not double the energy for hydrogen, this value is consistent with Model 1 and not with Model 2. In other words, the second electron in helium is in the same shell as the first electron. One last thing we should note before continuing is that ionization energy is a function of two variables, the nuclear charge and distance. From the ionization energy equation, we would expect that as nuclear charge increases and distance stays the same, ionization energy would increase. As the distance r increases and the charges stay the same, the ionization energy would decrease. So they work in opposite to each other. We'll now go on to look at other elements in the periodic table.